So we're going to look at a series of examples over optimization. Now, optimization is just a really common application of the calculus we've been studying so far from our curve sketching, in that when we think about optimization, we want to find maybe the maximum or the minimum value of whatever we're looking at. And that goes right along with those max and min ideas we've been taking from the first derivative test. Now, some examples that you might think of this would be like the greatest profit, the least amount of cost, the greatest voltage, something like that. That's kind of what we're considering here. So we're going to look at this first example, and it's pretty much a classic example. Says that we have a farmer has 1,600 feet of fencing, and he wants to fence off a rectangular field that borders a straight river. He wants to divide the pen into 4 equal sections, and with additional fence that he's going to place perpendicular to the river. So what we want to do is we want to find the lengths of the sides of the rectangular field, so we want to be able to maximize the area. Now I'm going to since I just read that, I'm going to highlight the idea that I am maximizing area. So I'll come back to that in a minute, but the first thing that you generally want to do is, if you don't have a image already provided for you, then you want to see if you can draw a picture of what you're given. So in this particular case, we know that we have this river here, and we have a rectangular pen that he wants to build. And he also wants to place inside of that some additional pins. So he's going to divide this into 4 equal parts. So we have 4 parts there. Now, we know that when we kind of need to put some labels on here, I am going to let the width of this pin be represented by X, and I'm going to let the length of the pen be represented by X, I'll call it, and the width here be represented by Y. So I have one width here of Y, but notice that I have each additional width here of fencing that he's going to place in there, which is the same value as Y. So all of these would be the same measurement. Now, if we come back up here and think about what it is that we are looking for, so I want to maximize area. And because that's what it told me. And I know that area is always going to be length times width, or in terms of what we're looking at here, it would be X times Y, because that's how I've identified the length and the width. Now, this right here, this formula, this formula that we're looking at, this equation that we're looking at for maximizing the area, is what we're going to call the primary equation. So let me just write that on here. This is our primary equation. And notice that I have 2 unknowns here in this primary equation. And so we kind of need to come up with a secondary equation. Generally, if you have 2 unknowns, then you have to have 2 equations. So the same number of equations for the number of unknowns. So we've got to figure out another equation that's also going to have an X and a Y in it that I can utilize. So if we turn back to the problem, it says here that the farmer has 1,600 feet of fencing. That's the only actual number that we're given in the problem. But if he has 1,600 feet of fencing, then I know that if I were to lay this fencing down in all of these places where I have X's and Y's identified, then that would be considered the perimeter. So in other words, the perimeter would be X plus 1, 2, 3, 4, 5 Y's, right? Because perimeter is the outside of things. So when I think of that, if I were to look at this equation and say, okay, well, I know that the perimeter, which is represented by 1x and adding that to 5y's, that's going to be equal to the 1,600 feet of fencing that he has available. So now I have an equation for x and y that's equal to a number. And this is what we would consider the secondary equation. So that's our primary equations, what we are going to maximize or minimize. And the secondary equation is what we're going to use to kind of substitute into that. Okay, so let's turn back here, or let's kind of continue on with our secondary equation that we have. What I ultimately want to do is I want to be able to rewrite this secondary equation in terms of one variable so that I can substitute it into the primary equation. So I am going to rewrite x plus 5y is equal to 1600 as either solving that thing for either x or for y. And we can see that it would be easiest to solve this equation for x. So I'm going to say x is equal to 1600 minus 5y. So I take the secondary equation, solve it for one of the variables so that I can then substitute back into the primary equation. So when I bring my primary equation down, let's bring it down here, we know that area is equal to x times y, but we're going to let x be replaced with 1600 minus 5y times the y I already have, and therefore my area is going to be rewritten in terms of only y's in this case. So I would end up with 1600y minus 5y squared. So far I haven't done very much except come up with an equation representing what I want to maximize, and I needed it to be written in terms of a single variable that I'm going to be able to use. Now, we know from the first derivative test that if I want to take a function and find out where that function has a max or a min, I would need to take the derivative of that function. So from here, we're going to take the derivative of a. So a prime looks like the derivative of 1600y would be 1600 minus 10y. And that is the derivative of a. So again, when we are finding the maximum or the min, we take the derivative and set it equal to 0. So I have 1600 minus 10y is equal to 0, and 1600 is equal to 10y. When I add 10y to the right, divide both sides by 10, and I find out that y is equal to 160. So this value here is the value of the max for my function of a, right? So a was in terms of the variable y, and I found out by taking the derivative what the maximum was going to be, because this is going to be a critical value, isn't it? This would be our critical value. Now we do need to test and make sure that this is indeed a maximum, and we can do that by taking that critical value of 160, and we are going to test the derivative a prime to the left and to the right of 160. So if I go in and I choose a value, say at 150, and I plug it into the derivative here, I'm going to find out that to the left of 160 I'm positive, and to the right of 160 I'm negative. So we are increasing and then we are decreasing on either side of 160. That means that this has to be a maximum value. So what we did find here, we've just proven, in other words, that this critical value of 160 is indeed a max, right? And we did that using our test values over there. So what I know now is that the length of one of these sides, the y value for one of those sides, is going to be 160. And now I want to find out what x is. So I'm going to come back here and I'm going to take my perimeter, my perimeter formula that we had. We know that the perimeter was equal to, and let me just write it like this, x plus 5y is equal to 1600. That's the equation that we know had a given value in it. I know that x plus 5 times 160, because I'm substituting in for y, is equal to 1600, so that I can solve for x. And this would be x plus 5 times 160 is 800, which is equal to 1600. Or in other words, x has to be equal to 800. So the question was asking me, what should the lengths of the sides of the rectangle be so that I have the maximum area, so I have the largest area inside of the fencing that we're given. So what we have is we have a constraint, right? We have a farmer who only has 1,600 feet of fencing. What's the largest pen he can build that would give him the maximum amount of area inside? And he was wanting to figure out what the dimensions that would be. And we found that the dimensions would be when y is equal to 160 feet and x is equal to 800 feet. That's going to maximize the area of his pen. So when we look at optimization problems, there is kind of a guideline that we're going to look at. We want to be able to identify all of those given quantities from within the problem, and if necessary, draw a sketch. Then once you have read through it, drawn a picture, you have to figure out what your primary equation is going to be. The primary equation is related to what you want to maximize or minimize. So in our case, we were maximizing area. So the equation related to area is length times width, or how we drew it, x times y. Then the second thing, or the third thing technically that you would need to do is you have to come up with a secondary equation that allows you to solve it for a variable so I can substitute into the primary equation. Okay, so just like we did up here, we had our primary equation for the maximizing of area, but what we were actually given in the problem had to do with when we had a real number we could solve for, right? We were able to utilize perimeter to be able to make our substitution. It may be necessary for us to determine what the domain of our primary function or primary equation is, just to make sure that we have fallen into just so we stay within that domain. And then finally, we would have to determine whether or not we found the max or the min. In other words, you're just basically coming back here and verifying, which is what we did here. We verified that our critical value of 160 was indeed a max.